Compton effect, as incident photon energy increases, scattered photon energy does what? And we had, as incident photon energy increases, scattered photon energy. As this energy increases, actually the energy to the electron starts to receive more dose. Remember there was a graph that looked like, something like this. It was a sigmoidal graph, and this was incident photon energy, and this was the electron energy. So this is photon energy, this was electron energy, and as photon energy, incident photon energy increased, the electron received more energy, and the photon received less energy. Okay. So then this graph is just the quantities in this graph are derived from the Compton equation. So if you plug in incident photon energies increasing, you'll get increasing electron energy and a decreasing photon energy. Okay. Okay, and then D, what else? E. Okay, as electron energy increases, the radiative stopping power. Okay, here's another graph. So this one here, this was radiative stopping power, and this is electron energy. And there are 6 curves on this graph. There's 3 curves for the different materials. One material was, if I remember correctly, copper. Then there was a soft, I think there was a tissue in there, and I can't recall what the third one was. And the collisional stopping power did something like this for the different materials, and the radiative stopping power did something like that. Here, remember that? And this crossover point was at a pretty high energy. I believe it was around 10 MeV. Okay, so this is a curve that you should also have in mind. And this is collisional stopping power, and this is radiative stopping power. Okay. And so what this is telling us is the stopping power, the collisional stopping power, is a lot higher for lower energies. Okay, so we'll tend to see a lot more. We'll tend to see materials absorb energy through collisional losses much more readily than radiative losses at low energies. Okay. But as the energy gets higher, then we start to see more energy loss or energy absorbed in the material through radiative processes, and especially more for higher Z materials. So this would be the higher Z curve. This would be the lower Z curve. Okay. What letter was that? Okay. What else? Any others? Should I go to the problems then? No. Everything else okay here? Okay. All right. Calculations. Let's see. So I know this was a while back, but it's not a bad time to refresh our memories, right, on all this stuff. So TG51, given R50 is 3.5, calculate dref. So basically, you just have to memorize this formula. Okay, there's certain formulas that through this course that I require you to memorize. For a cerebrum block of thickness 7.5 and transmission of 3%, calculate linear attenuation coefficient. Okay, again this equation you need to memorize, and this is the basic linear attenuation coefficient exponential attenuation equation. You can start with I equals I0. Maybe I should zoom this up a little bit. I equals I0 e to the minus mu x. I0 is intensity before the block, I is intensity after. So mu, you can rearrange the terms by taking natural log of both sides, then rearrange the terms, and you get I over I0. We know it's 3%, so it's 0.03 divided by x, and x was 7.5. And I don't know if I gave this number. I might have not given it, but you could have just put it on. I mean, you should know that a cerebrum block is 7.5 cm. Okay. If you didn't know, you could have estimated it. Okay. If you put x in there, I gave you that question. I didn't expect you to remember that, but you should know that it's 7.5. If the dose rate at 80 centimeters from the source of radiation is 100, what is it at 120? So that's just basic inverse square law. And number 4, TG51, the diameter of a chamber is 0.6. How much shift do you need to make So you need to know what the shifts are for photon chambers, in other words, cylindrical chambers. Sorry, not cylindrical chamber. You need to know the shift between electrons and photons. For photons, it's 0.6 arcAv. For electrons, it's 0.5 arcAv. And arcAv, the diameter is 0.6. ArcAv is 0.3, because the rays have the diameter. So 0.6 times 0.3 is 0.18. Okay, next question. If optical density of 0.3 is given, calculate the transmission. Well, the optical density is defined as the log of 1 over the transmission. So we can raise both sides of the equation because we want to isolate the transmission. That's what you're solving for. Raise both sides of the equation to the power of 10. Okay. So 10 to the log is just the argument, and then 10 to the OD is the other side of the equation. Then solve for t, and t is 0.1%. Okay. Next question. Given that air requires 33.85 joules to create 1 coulomb of ion pairs, how much dose is deposited in air at standard temperature and pressure with 1 Roentgen of radiation? And I give you a hint: 1 gray equals 1 joule per coulomb. But you guys know that. So then the definition of a Roentgen is 2.58 times 10 to the minus 4 coulombs per kilogram per Roentgen times the number of joules per coulomb that is created when you create an ion pair. Then you multiply this, the coulombs cancel here, and you're left with joules per kilogram per Roentgen, and joules per kilogram are gray, so I converted joules per kilogram to gray, the units here, so you end up with 0.00873 gray per Roentgen. Section 2, problem set. Stop me if you have any questions. I might be going a little fast, but. For 200 keV photon interacting with material scattering away at an angle of 30 degrees and then interacting with another atom through photoelectric effect. So there's a couple of things going on here. 200 keV photon scatters through Compton at an angle of 30. Whenever you see an angle, think of Compton, because we can use angles in the Compton equation. Then that scattered photon interacts through photoelectric effect, and no angles required there. Calculate the energy of the scattered photon and the energy of the electron ejected through the photoelectric effect, and I give you the binding energy because you need that for photoelectric effect. So we'll start with the Compton effect. So the scattered photon h nu prime, we want to know what that energy is. We know that h nu naught is 200 keV. We know that this angle is 30. Cos of 30 is 0.866. Run that through the equation. You get alpha equals h nu over m naught c squared, which is 0.39. So h nu prime is 200 times this quotient. You end up with 190 keV for the scattered photon. Then the energy of the electron that's scattered through photoelectric effect is your scattered photon energy minus the binding energy. So that's 150. Okay. Number 8. In electron therapy, calculate the monitor units for a given dose of 200 centigrade, photon factor 0.95. A cutoff factor of 0.94 at 100 SSD, an effective SSD of 89, Dmax is 2.1, and the treatment distance is 110. Okay. So because you're not treating at 100, bing, you should know right away that you've got an inverse square factor involved. Okay, so you can calculate that off the bat. The inverse square factor is equal to, and you need to know this equation, it's your effective SSD plus Dmax divided by effective SSD plus Dmax plus your gap. What's the gap? What's the definition of the gap? It's not 110. Some people put 110 in there. It's your treatment SSD minus your nominal SSD. Treatment SSD is 110. Nominal SSD is 100. So your gap is 10. Square both. You get 0.812 as your inverse square factor, and your cone factor is 0.95. What's the cone factor defined as again?
The comparison of your size cone to the reference.
Correct. Your treatment cone and to what's a typical reference cone size? 15 by 15. In this case, I don't tell you what your treatment cone is, but I tell you that your cone factor is 0.95. So you know that your treatment cone is not going to be 15, right? By 15, because it would be 1. This would be 1. So this could be a 10 by 10 or 6 by 6 or whatever. Okay, and then what about a cutoff factor? What's the cutoff factor?
dose rate difference between having cutout and without that.
Right, so it's your treatment cone with cutout divided by your treatment cone. Okay. Okay, effective acetate, put all that in there, inverse square. Here your dose, your MU equation is here with dose on the numerator, and then 1 centigrade per mu, your cone factor, cutout factor, and inverse square factor, and you get 276. Number 9, from TG51, chamber is A12. Got all that data, I'll give you all that data. Oh, look, these little marks stayed on there. I'll give you all that data, so you're required to do TG51. Basically, you have to know these equations. So this question was really plug and chug. I think you guys got it. You might forget a term here and there. For the most part, you're okay with that. Okay, calculate KQ. So from the very, you have to go to the KQ graph and look up the KQ. Any issues with looking up the KQ with that graph? You don't know how to use that graph, right? There's H curve is a different material, and because the numbers here are so, I mean, there's so many scales between such a small interval in number that you can get a pretty accurate measurement of what KQ is here. So you can read off the graph pretty accurately. If you don't like the graph, you can use the table in TG51. Okay, so then dose per mu in this case was 1.0137. Okay, moving on. Assay question. I don't know if I have the answers to the assays here. I think I did. So the first assay question was, come on, Windows. Draw a schematic of the interactions that take place when a photon interacts with the material and sets electrons in motion. Use the drawing to explain how terma creates absorbed dose and define the intermediate terms. So I wanted you guys to show this interaction. This is an important schematic right here. It tells everything that's going on as photons interact with electrons and then the cascade of particles and energy. So terma is equal to total energy release in the material. So the terma is the energy released by the photon in the material with the first interaction. Kerma is a kinetic energy given to the electron or positron in the material. Okay, so kerma is after this first interaction, some gets scattered away, and kerma is the energy that this electron takes. This is an important factor because this might scatter outside the patient. The scattered photon might leave the patient, and we're not concerned with that. Although treatment planning computers do consider terma, because there's a probability that this might scatter inside the patient and create more electrons. So we do have to take that into account in treatment planning. Collisional kerma is the kinetic energy absorbed in the material. So then after this electron absorbs some energy and travels through the patient, a proportion of it leaves as radiative kerma, and a proportion stays in the patient, and that's collisional kerma. Okay. So I mean, we know how much gets scattered here, and we know what the proportions of that get scattered here. So this is actually very low, right? The radiative kerma is extremely low in tissue. Okay. It's higher in high Z materials, but in tissue it's extremely low. So this is almost negligible, this radiative kerma. This part right here is not negligible. Okay, and then terma is greater than kerma, which is greater than collisional kerma. Explain two measured functions of a guard electrode. Explain what would happen to the signal if the collecting electrode were shorted to ground. Draw a schematic of a cylindrical plane parallel chamber. So the guard electrode provides a path for leakage current to go to prevent it from interfering with the signal. Right? So that's the first thing. It defines the sensitive volume as well. If we didn't have a guard electrode, remember how the electric field lines could bow out and we would have an uncertainty in terms of the collecting volume? So by creating a guard electrode, we are creating our volume. We are defining our volume, our sensitive volume. And part B was explain what would happen to the signal if the collecting electrode was shorted to ground. Well, Here I'm going to draw the schematic, just a simple schematic of a plane parallel chamber. Okay. Battery, 300 volts typically, goes to ground. And the collecting electrode goes through your electrometer or ammeter to ground. And this is the guard electrode. So guard electrode goes to ground, collecting electrode goes through an ammeter to ground. So if the signal signal in the collecting electrode were shorted to ground, what happened to my drawing? I gotta redraw it. There's a. Okay. What's this electrode called at the top? What's this one? It has a name. Polarizing electrode. Okay. That's where you apply the bias. 100 volts. Okay. So anyway, so if this was shorted to ground, if we did this, we wouldn't read anything, right? On the ammeter. Because all the electrons would go through here, all the ions would be collected, and then they'd go into ground, so we wouldn't read anything. Okay? So it would be low, very low because it wouldn't be read by the electrometer. Explain the advantage of placing lead polymation directly on patient's skin. Explain the unintended effects this may cause, the patient and method that can be employed to avoid them. So placing lead right on the advantage of placing lead right on the skin is that it creates a very sharp penumbra. Okay, the penumbra is not that great for this is for electron therapy. So the penumbra is not that great for electron therapy, and especially as you go further away, the electrons scatter more laterally, and it makes the penumbra worse. So we often, when we have extended SSDs, we often use lead on the skin to create that sharp penumbra. Great. So do you put lead straight on the skin? No, because you can get electrons and low energy photons scattering off the edge and create this hot spot right at the edge. So what we do is we wrap it in wax, and wax absorbs low energy electrons and low energy photons. So the primary Z, putting high Z materials on the patient is a high number of secondary electrons and photons. Should be sheathed in low Z materials such as wax. Okay, so that's what I was looking for. Describe chamber collection efficiency. What physical parameters affect collection efficiency? What are the related equations? So this is, we talked about collection efficiency for a little while. Remember Boag, B-O-A-G, has a theory, and we base most of that on his theory. So collection efficiency is the ability of a chamber to collect ions. Chamber geometry, electric field, dose rate, and internal ion recombination all play a role in collection efficiency. So it's defined as the ratio of collected ions to created ions. So I wanted you to know this equation or something close to it. So the C factors has a constant, and it's important to know this equation because if you know the equation, you know what parameters affect collection efficiency. So here's V, so voltage across the plates affect collection efficiency. The distance between the plates, and that's because as you make the distance bigger, the chances of recombination go up, and your collection efficiency goes down. Again, voltage, if the plate voltage is really low, then the ions don't experience much of a force. And if they don't experience much of a force, it increases recombination probability also. And then Q is the amount of charge that you collect. So obviously that affects collection efficiency because the ratio of collected ions is right in this equation. So you put that C into this equation, and you get F, okay, which is the collection efficiency, and that's for plane parallel chambers. And then this graph here converts the D in this equation for plane parallel chambers to a D of cylindrical chambers. And that is represented as the parameter d sub CYL down here. Okay, and then what you do, remember what you do here is you have to know what your A and your B is for your cylindrical chamber. You get the ratio of A over B. Look up the K in this graph for a cylindrical chamber, and then the D is equal to the K that you look up times the D CYL. And unfortunately, this text isn't coming out. Okay, and I think this should be a lowercase d right here. This capital D, that should be lowercase d. And it should go there. And this should also be lowercase d. You know, sometimes Word capitalizes things for you. You're typing away and it just, because it's the first D. So these should be lowercase. And this D is the same D as this D up here. Okay. So you calculate your DCYL from A minus B of your cylindrical chamber, put that in here, multiply by your K, and then you get your D, which you can put in here. And that's how you get your collection efficiency for a cylindrical chamber. If you have a plain parallel chamber, you can ignore all this, go straight to this. Bonus. In a TLD glow curve, what does each peak represent? Glow curve looks like this. So this is temperature, and this is light output. Okay, and it looks something like this. Got a couple of peaks that look like this. There's a high peak. Sometimes there's a peak over here at the end. There's always a peak at the end. And remember that we typically use lithium fluoride 100. That's a particular kind of material that we typically use, and that's one of the most common ones. But there are other kinds of lithium. There's lithium fluoride dash other numbers, and there's other materials too. And the glow curves would be different for each one. So for lithium fluoride 100, we have 5 peaks. Each peak represents the trapping energy level. So those are the forbidden. Those are the energy levels inside the forbidden gap. The forbidden gap is that gap where electrons are not allowed to live. Okay, they're not allowed to be trapped in. But when we put impurities into crystals, we create these trapping centers. Okay, so depending on the distance from the trapping center to the atom's nucleus, that establishes the energy level. So the first peak down here is the one that's closest to the conduction band and furthest away to the nucleus. And trapped electrons are most readily released. And because it's furthest away, they're most easily released. So as the temperature increases, right away they get released and they create light output as they drop down to lower energy levels. The 5th peak is the most populated and has the most traps. It's also closest to the nucleus. So this one here is the electrons that come out at this temperature are the ones that are most tightly bound. Those are the ones closest to the neutrons and protons in the middle. Okay? And also, because this peak is the highest, it's most numerous. So most of the electrons are trapped in that energy level. I described the annealing process. That's part B. The annealing process removes most of the electrons from their trapping sites. And so the annealing process is what you do after you've read it. Then you put it into, remember the 2 ovens I talked about? There was a low temperature oven and a high temperature oven. Okay, and first, the low temperature oven, the first step is the high temperature oven. That's the 400 degrees C. You put it in there for 1 hour. That releases most of the electrons. And the second step, you heat the chip to 80 degrees C for about 30 hours. So you leave that overnight. And that removes the ability of the chip to deposit electrons into low energy. So it puts the chip in a certain state. And it puts it in a state where it doesn't accept electrons in, well, I'll say that this is the first peak. It doesn't accept electrons in the first peak. And that peak, if you don't have that peak, it's a good thing. Because that peak is, it's a little not very reproducible. Okay? Because that peak will change, the height of that peak will change depending on when you read it. If you read it right away, that peak will be high. And if you wait to read it, some of the electrons will just naturally come out of their traps and it will be low. Okay, so there's a little uncertainty in that peak. Doing this second step reduces that peak. And actually, it reduces some of the other peaks. And the ideal glow curve looks like, almost like a Gaussian curve. It looks like that, where it has 1 peak. That's what you want. Okay, so that's the annealing process. Okay, next. Any questions? Let's go to the midterm. Oh, I guess it was thinking. All right, midterm. Anything in here in the first section? G. Zero field TAR does what when mu, linear attenuation, increases? Okay, zero field TAR when mu increases. No, zero field TAR, that's only affected by primary photons.
Yeah.
So as mu increases, and TAR is the dose in tissue divided by the dose in air. Okay, so if mu in the tissue increases, what does that do? That reduces the amount of transmitted photons, okay? And that should also reduce TAR. Okay, because then if there's less photons at a particular, remember TAR is depth dependent as well. If there's less photons at a certain depth, then the dose here, and compared to the dose in air, the mu does not affect the dose in air. Okay, it's only going to affect the dose in the tissue. So if mu increases, that means that attenuation increases, that means that dose decreases. Therefore, the dose in tissue is going to be lower than the dose in air. And since TAR is defined as dose in tissue divided by dose in air, then TAR will drop. Okay. And there was a formula for that in one of the slides for the TAR. Okay, that's G. What else? What about I? Everybody get that? MUs. What happens when you decrease wedge angle to the MUs? MUs decrease? Yeah, because you want to get the same dose. Remember, you're just changing wedge. So you decrease it, you don't need as many MUs. Okay, that makes sense. Beam gets hardened when the beam hardening decreases when you decrease wedge angle. Again, there's less metal in the way. Wedge factor decreases with an increase in wedge angle. So as you go from a 45 to a 60, you expect your wedge factor to drop. Beam weighting should be okay. Beam weighting should always be less for the beam furthest from the tumor. Skin gap increases with field size. Okay, you can kind of write that equation down if it doesn't make intuitive sense. Okay, couch kick. Okay, and a DVH, increased steepness of the curve, it means increased tumor coverage. We talked about that. Adding bolus obviously increases skin dose because it decreases skin sparing. Dose near the anterior part of the breast with an increase in wedge angle. So if the wedge angle increases, say from a 30 to a 45, then the dose near the anterior part drops because the heel gets thicker. That's where the heel is. Okay. S sub C question. We know S sub C increases with field size. S sub P also increases with field size. And as SSD increases, you get further, so your MUs have to increase to keep the same dose. Any questions on this? Okay. Problems, short answer questions. Calculate MUs to deliver 180 per day. So these are photon. You have to look up a TMR. Oh, this is the one I didn't give you guys a TMR table for. You said you had to memorize the table, right? I needed a page me right away, and I got it to you. So there's your TMR. S sub P is 1 because it's a 10 by 10. There's the MUs. I think you guys all got that one. Well, this one here, I think somebody got confused about the 40% block. Remember, there's blocked and there's open. Okay, we need to know the open. We need to know what the open field size is when we're going to use this equation. So the open field size was 60%. So 60% times 5 times 12, those are the dimensions of the field. Let's take the square root, that's a block equivalent square. And then TMR, remember, use the block equivalent square for TMR. Don't use the jaw size, it's the block size. And then you need to, whenever you have a block, you need to separate your S sub C's and your S sub P's. So S sub C for 7, because that's the, let's see, 7, why is it 7? Oh, 5 by 12. I was looking up here. It's 5 by 12, so equivalent square is 7. Block is 6, so S sub C for 7 and S sub P for 6 because you use a block square for S sub P. Okay, and uses 194. AP field and SSD setup, 20 centimeters deep, use TMR tables. So the SSD is 100, the depth is 20 centimeters, so the point of interest is how far from the source in this case.
It's 120.
Right. So always, when you have a question like this, always think about where's my point of interest. A lot of people forget the inverse square, and I should tell everybody at the beginning of the year. You will forget your inverse square factor at some point. Okay, so whenever you're presented with a problem, always think about how far is my point of interest. If it's not 100 and it's an SAD calculation, it's an SAD calculation because it's what you use TMR tables. Remember that there's going to be an inverse square calculation. Okay, so you're 120 centimeters away. You can calculate inverse square right away. In this case, it's 0.694. The other thing you need to consider is the field size is going to be bigger than your jaw setting, okay, because it's 20% further. So you've got to calculate your field size, and here it is. It's 10 times 100 plus 20 over 100. So your field size at your point of interest is 12. Depth, you know, it's 20 centimeters. And then again, since the field size at your point of interest is not going to be 10 by 10, it's going to be 12 by 12. Then your S of P has to be for the 12 by 12. S of P is always the field size at your point of interest. Okay. S of C only depends on collimator setting. Think of S of C only depending on those digital indicators on the machine. It doesn't depend on field size at the point. Because this S of C depends on two things. What are those two things that S of C depends on? Remember, that's the scatter correction factor or scatter output factor.
The field size and the energy.
Depends on the collimator setting, right? Energy, what else? Yeah, it does. But it also depends on how much is scattered into the myonuclear chamber, right? Yeah, okay. So MU is 180, inverse square factor is here, inverse square factor is here, and then 0.629 was the TMR for a depth of 20. 1 is the S sub C, and 1.08 is S sub P. Okay. Next question. What is the wedge factor through an off-axis point on a 60-degree wedge whose thickness is 1 cm at that point? So I give you a thickness, and I give you a linear attenuation coefficient. So right there, you have to think, well, maybe I should be using this attenuation correction formula. So the wedge factor is equal to e to the minus mu t. Mu is 0.25, t is 1. So wedge factor is 0.779. I think you guys all got that. The field size in there, 100 cm from the source, 10 by 10. What is it? 100 centimeters away, 120 centimeters away rather, and it's just 12 by 12. The field size in air at 80 centimeters is 12 by 20. What is it when 120 centimeters away? Well, both dimensions have to increase as you get further away. So since both dimensions increase, the first one is, well, the ratio of the increase is going to be where your destination field size is compared to the field size where the field is given. Sorry, the SSD where the field is given. That's 120 over 80 times 12. So this dimension goes from 12 to 18. And then here's the same ratio for the 20. This dimension goes from 20 to 30. So the field size is 18 by 30. The radiation exposure in air is 80 centimeters away is 100 ml per hour. What is it at 120? So that's just basic inverse square calculation. If the PED for a 10 by 10 at a depth of 5 is 92 and the dose at 5 cm is 100, what's the dose at Dmax? So again, that's just, you know what the definition of PED is. It's just dose at depth divided by dose at Dmax. Okay. Given the following information about CNS, PA spine is that lateral field is 18 by 12. The tricky part here is really, so the question is calculate collimator angle for the laterals to reduce beam divergence into the spine and calculate couch kicks. The tricky part here is remembering that this is the X jaw and this is the Y jaw, and which ones are the ones that you need to use for your angle calculations. Okay. So collimator angle is arctan of the field size divided by 200. So for the collimator angle, the field size that we want to use is what? It's not the lateral fields, right? It's the PA spine field. Is it 5 or 36? It's the 36. Okay, it's the long one, and because that's the one. Here's the PA spine. Here's 36, and then the angle that we're looking for. The angle that we're looking for. Get it closer. Yeah. Sinclair, I'm afraid if I close that, save it. So the angle is this angle right here. Here's the collimator. So it's the angle that we're looking for is this angle right here. So then it's gonna depend on this angle. So it's arctan of 36 divided by 200. The couch kicks will depend on the divergence of this field right here. Okay, so you need to know this dimension. So 18 by 12. Well, 18 by 12, x is 18. Okay, now which one's x? Is it this one or this one? Is it this one or is it this one?
Yeah,
This one, that's x? Well, we know that this is x and y, right? Because that's convention. It's always x by y. So, but out here, do you think this is x? To me, you know how I figured out? I always think of what it looks like with a 0 degree gantry. So I kind of bring this up to 0 degree gantry and I go, okay, now I'm looking at it as the beams I view at 0 degree towards my x. And if I imagine, that's what helps me. If I picture it that way, then I can say this is x1, x2, y1, and y2. Okay. Picture it that way. All right? Does that make sense? Because the gantry rotates in this direction.
yeah.
Right? Patient's lying down here. Patient's prone, lying down here. Okay, and the gantry, what's the gantry angle for this beam?
Okay. 90.
90. It's a lateral, yeah. It's a left lateral. Well, the patient's prone, so it's a right lateral. Okay, because the patient's prone. Oh. Why is it doing all this? Did I do this something differently? Oh, maybe because I'm using Word. Okay, so you need to, so if that's the case, you need to use this dimension because that's the dimension that diverges into the other beam. Okay, so you need to use the y. Okay, is that what I did? The 12. Yeah. Okay, so use the 12 or 200 for the couch angle. All right. Number 4, I give you a drawing of a source irradiating a patient. In the diagram above, 10 MV, 10 by 10 SAD irradiates an oval structure. The dose to the isocenter, the plus symbol is 200 at a depth of 10. Point A is 20 centimeters deep and 6 centimeters off axis. I give you an OCR ratio. OCR just is off-center ratio. It's the same as OAR, off-axis ratio. What is the dose at point A? So TMR for 10 by 10 is here. Field size at point A is, since A is a little further, the field size is a little bit bigger. And the TMR at a depth of 20 for that field size is there. Again, since A is not at 100 centimeters, there's an inverse square factor right here, 826. Okay. So the dose is equal to 200. And this is just basically the MU calculation rearranged. Remember, MU equals dose divided by dose rate? That's what this is. So I just rearranged it. So I have MUs over here times the 826 is 826 is the inverse square factor. 6245 is the TMR to 20 cm depth divided by the TMR at 10 cm depth, because we need to do a ratio of TMRs, times 1.008, and that's the SFP ratio. It's SFP 20 divided by SFP 10, so it's greater than 1. SFP 20 is bigger than SFP 10, times 1.02, which is, the OCR, stop axis, and you get 126.5. Okay. Okay, so whenever you get a question like this, when you know the dose at one point and you need to calculate the dose at another point, remember that the TMR ratio is going to come into play. Okay, unless one of the doses is Dmax, then the TMR is 1. Okay, then that's a little easier. Okay, but when you have two depths like this, like a 10 and a 20 or 10 and a 12, then you're going to have to use the TMR ratio to calculate the difference in doses. Okay, DVH, this is pretty simple. This is just a graph lookup. I explain the advantages and disadvantages of SSD and SAD setups. So SSD, advantages, easy to set up to an SSD with an ODI. Okay, so it's easy to use the ODI. I was just going through, there's a website that you can find. It's called ROSIS, ROSIS, and that's a registry of all the radiation oncology errors that occur all over the world. People can just go on there, you can log in, create an account, and if there's an error in your clinic, you can go, anybody can do this, they can post their error with the information. So it's a huge database, and one of the errors that happens quite often is SSD setups, because people aren't used to doing SSD setups, they're used to doing SAD setups. So when they set up a patient with SSD, they incorrectly set up the patient. And one error was where the patient was being set up SSD, but it was a PA field. Okay, so at the PA field, you got to measure an SSD, so you got to look at the ODI under the table. That sounds kind of tricky, right? Because the table, first of all, the table doesn't represent the patient's skin. That's first of all. Okay, some tables are really thin, or you're treating through the tennis racket. You know the tennis racket, what we call the tennis racket. So the tennis racket isn't really thin, isn't really thick. So maybe the tennis racket represents pretty close to the patient's skin. But the tennis racket is dark, and it's crisscrossy. And so reading the ODI on the tennis racket is challenging. So a lot of therapists will put the ruler up there and read that. But they're holding the ruler, and the ruler could be at an angle. Okay, so one error that I found was SSD setups and incorrectly reading the SSD, especially for PA fields. I just found that when I'm thinking of pros and cons of SSD setup. So one con is incorrectly reading SSD and doing something that they're not used to doing. So SSD, easy setups to an SSD with the ODI. Disadvantages may require the Maynard factor correction for every SSD, for every field. There's 3 calculation variables: field size, SSD, and depth. Yeah, depth. More MUs are required for SSD setups because the patient's further away, longer treatment times, since the point of interest is further from the source. Decreased dose from scatter, and one advantage is that there's decreased dose from scatter from the jaws. If the patient's further away, then there's less scatter dose given to the patient, right? And so this is something to consider when you're treating patients with breast cancer, because doctors are always concerned about the contralateral dose. You know, the healthy breast, the contralateral breast dose. The healthy breast should not be getting any dose because you're not treating it. There's no cancer there. So if you can treat a patient with an SSD setup, then that contralateral dose is going to get less. Contralateral breast is going to get less dose. SAD, pros, only 2 variables to worry about. That's depth and field size. Cons, less clearance with gantry head. Okay. All right, number 7, from the sagittal slide of our class lecture, explain possible problem with opposing treatment fields. So what's the possible problem with this? The problem is that if you're doing, if you look at a DRR, this AP field, this anal marker, which is what the doctor put a marker there because he wants to treat that, he or she wants to treat that. They put a marker there and it looks fine, and then they say, well, just oppose that field and make it a PA field. Well, if you just oppose that field, since your isocenter is anterior to the marker and you just oppose it, that field is going to be smaller than you want it to be, and therefore you're going to miss the marker with this field. Okay. And of course, that's not all you're treating. You're treating all of this, but that's the most inferior point, and the doctor wants to include that in the treatment. Okay. Number 8, for 3 fields, single isocenter breast treatment on the right breast, no collimator turns. I just explained the position. So I wanted you guys, just from a feeling, just from intuitive feeling, just describe what these jaw sizes would be. So on a medial field, if it's a right breast, okay, so I'm treating this way, medial field is coming in this way, what's X1? So if it's a medial field, let's look at beam's eye view. A right breast, beam's eye view is going to look like this, and the breast is going to look something like that. So here's X1. That's not right. This is Y1 here. Y2 here. Okay, so medial, X1 is flash. This is flash right here. X2 is 0, right? Because it's a half beam. I put it across here, but really, if it's half beam, our isocenter, it doesn't look like an isocenter. Our isocenter is going to be right here by X2. Y1, okay, what about Y1? So Y1 is going to be the inferior portion of the field. Y2, if it's a 3 field, we want Y2 to be, so the isocenter is really up here. I was too quick with the isocenter drawing. I think it's inserting these drawings into the Word document. That's what's happening. And then it just stops. There goes my drawing again. Well, now I know it's done because it's putting it into Word, and there's no page out here. Okay, so the whole thing's gone. Let's get my drawing. Isocenter here. Y2, X1, breast, Y1, and X2. Okay, so X2 0, Y2 0, because this one has to abut to the supercloud. Okay, any fields that abut, you want to make them 0, so there's no divergence. Okay, and then the lateral field, and so that lateral field's going to, I guess maybe I should draw on a page. The lateral field's going to look like this. Breast is on this side now. Okay. And the lateral field comes in this way, so X1 is going to be 0, because isocenter is going to be up here now. X1, X2, this is Y2, this is Y1. Okay? So lateral, X1 is 0, chest wall, X2 is flash, Y1 is inferior portion, and Y2 is 0, because it's going to butt to the superclave. And then superclave looks like this. It's a right breast, so the isocenter is going to be down here. Okay, and this is going to be X1, Y2, Y1, and X2. Let's see if I got that right. So X1 is open. X2 is small or 0. So X2 might be slightly open. So X2 small or 0. Y1 is equal to 0 because this has to butt to the tangents, and Y2 is the superior portion. That part's open. Okay, makes sense? Okay, draw an axial view of breast showing the position of tangent fields and the isocenter. So I wanted you guys to draw something that looks like this. With an isocenter here. And show me some flash. What's the typical flash? 2 cm, right? 2 cm, and then how much lung do we usually treat? How much lung do we usually treat? 2 cm lung, typically. 2 cm lung. Why do we treat lung? There's nothing in the lung.
The breast moves, the respiration.
Right, respiration, yeah. Could be respiration. What else?
The chest wall.
Yeah, there could be some involvement in the chest wall. And the chest wall, these are the ribs. There could be some tumor near the chest wall. So we want to treat the chest wall too. Okay, tangent fields, field edges. So this is one field edge here. This is another field edge here. Okay, that's your table that I didn't give you. Is that it? All right, any questions? Did all that stuff come back from the final exam? It's fresh in your mind? Okay, let's take a break. You guys can keep those exams. Save changes. And then when we come back, we're going to talk about electrons. I know we talked about electrons already. We're going to go into a little bit more depth today. All right, let's talk about electrons. So we talked about electrons briefly in terms of monitoring unit calculations and output factors, cutout factors. This lecture goes into a little bit more depth. So we'll move quickly through the stuff that we've already covered, and I will cover some new stuff here too. So electrons, this is just a picture of Monte Carlo simulations of how electrons scatter in tissue. This is another one. Hard to see with the lights on, but so this is Monte Carlo simulation, 6 MeV electron beam incident on 2 different carbon targets. So this is the kind of output that Monte Carlo simulations will give you. They give you an idea, but this is a visual representation of what's happening to those electrons. Remember how I say they scatter off quite a bit? So there's a lot of lateral scatter that you can see from this picture. So basic concepts. Let's just go through some bullet points about electron properties of electrons. They're inelastic collisions. Well, there's 2 types of collisions. So there's inelastic collisions and elastic. The inelastic collision means that the original kinetic energy is used to ionize or produce photons, like bremsstrahlung. The elastic collisions means that the kinetic energy from the electron is transferred to other particles. Okay, so think of elastic collisions as billiard balls, okay, and think of inelastic ones where the energy is transferred to a different type of energy. So it's transferred from kinetic to photon energy. That's inelastic. Collisional losses, mostly low Z materials such as tissue and water. Radiative losses are proportional to Z squared. Okay, so if the material has a high Z, it's going to have more radiative losses. Rate of collisional energy loss or mass stopping power is higher in low Z materials than in high Z materials due to more electrons per gram. See figure 14. Electrons are more tightly bound in high Z materials. So it seems that the collisional energy loss seems counterintuitive, that the low Z materials actually absorb more electrons than high Z materials. They do for the collisional energy losses. So the collisional part, low Z materials do absorb more electrons than high Z materials. Because there are more electrons per gram. Remember that factor, electrons per gram. And you can look up the number of electrons per gram in the back of Kahn or in the back of Johnson-Cunningham for the different materials. So as Z goes higher, the electrons per gram drops. And another factor to consider is electrons are more tightly bound in high Z materials. Okay, so they require more energy to be ejected. This we covered, right? Remember this? E sub 0 is 2.4 times R50, average surface energy. So that's the average energy as the electrons hit the surface. TG25, we learned that E sub Z, which is the E at a certain Z, Z being depth, at a certain depth is equal to E sub 0, which is this factor up here, times 1 minus the depth divided by the practical range. And in TG51, we learn more things. We learn that R50 can be described by this equation. If we had I50, where does I50 come from? Yeah, from measurement, ionization depth dose. And so this equation is good for 2 to 10 cm for I50 of 2 to 10 cm. And then there's another equation for I50 is greater than 10 cm. And linear calibration of dose per mu is done with TG21 or TG51, either one or the other. Of course, I would encourage 51 because it's newer. Electron beam therapy, basic concepts. So electron beam therapy is used for superficial or shallow disease. Total electron skin therapy, where the entire surface is irradiated. One example of a disease that you would treat with total electron is mycosis fungoides. This starts in the lymphatic channels. It's a lymphoma. Have you guys seen, anybody seen, maybe a Lutheran? Have you guys seen total skin? A Lutheran? You haven't seen it yet? Okay. It's not very common. Also used for breast boost. Keloids. Who's seen keloids? Anyone see keloids yet? What's a keloid?
It's like a scar.
Yeah, it's like a scar, right? A scar that grows very quickly. It's kind of large. And so we treat them for larger scars. We usually treat them before the scar gets formed, because once the scar is formed, it's too late. We treat them as soon as the incision is made and the patient recovers from the incision. Then we go in and we treat that incision so that we don't have excessive scar form. And so radiation reduces the amount of excessive scar formation. So that's keloids. Non-cancerous. Keloids are non-cancerous. So we often, typical ones we'll see is earlobes. Okay. And why? Because somebody gets their ear pierced, and for some reason this person has a genetic propensity to create a lot of scar tissue, and they develop this maybe a chickpea-sized keloid, and they cut it off in surgery, and then they come to us for radiation. Of course, keloids can happen anywhere in the body. Make electron trees for fun, right? Always use with SSD setups, never SAD because they don't penetrate deep enough. We always use them with applicators or cones to collimate or flatten the electron beams. There's a sharp dose fall off at RP, the practical range. Right? And Linux can produce several energies. So there's usually 5 energies on a Linux. Oh, by the way, that's a picture of a Mobitron. A Mobitron is a mobile interoperative linear accelerator. And typically these linear accelerators have only electron energies, and they're used in the operating room. And it's used for intraoperative radiation therapy. So one example of this would be if somebody has cancer down in the abdominal cavity, and the surgeons go in there, they open it up, they take the tumor out, but then they need to irradiate the tumor bed to make sure to kill the rest, any kind of residual cancer. So they'll come in with this Mobitron after the tumor has been removed, and put an applicator right into the cavity and irradiate, give the patient 1 dose of electrons. That's called that. If you guys listen to NPR, the Cancer Center Treatments of America has been advertising intraoperative radiation therapy. So, and I've heard the ad multiple times now, so maybe they just got it and they want this advertisement out there. Measuring electron PDDs. Okay, we've all done this. Maybe once. Multiply with chambers. You have to multiply the measure ionization by P repel for energy E sub 0 at each depth. And then you also have to multiply by the linear energy transfer, or the L is the restricted stopping power ratio between water and air. Okay, and then with diodes, you don't have to correct this because the water diode stopping power ratio is constant over all depths. Okay, and the reason you need to multiply for chambers is because of this ratio here changes with depth. Okay? So if you're measuring an ionization depth dose, you're measuring it at different depths. That's the definition. So at a different depth, you're going to have a different L over rho. You have to multiply the different L over rho's for every depth. With diodes, this number is constant. So that's just the number that you multiply to get dose. Oh, you don't need to multiply because PDDs are relative. So anything relative drops out, so you don't even need that. You only have to multiply it if it changes with depth. Film, H&D correction is necessary. This is all under measuring electron PDDs, chambers, diodes, and then film. So with film, H&D correction is necessary. That's the characterization curve. With film, it's quicker than scanning in a water tank because you could place the film edge on and you could shoot it, and you can just irradiate it with 100, 200 monitor units, and you've got a PDD. Of course, you have to scan it afterwards, so I don't know if it's that much quicker. Can be used perpendicular or parallel to beam. And care with setup is essential. In Con Figure 14.6, it has some. Oh, you've got Con. Let's go to Figure 14.6. It has some issues that you could run into if you don't place the film correctly. Someday all these books will be electronic, and I don't know how a little icon I can double click on. So here's some issues that you can run into. It's in page 3 of this version. So these are the different, so this one here, film artifacts created by misalignment of the film and the phantom. So in graph A, air gaps between the film and the phantom. So usually the phantom is 2 blocks of solid water. You sandwich the film between them. So if there's an air gap between the film, you'll get this issue here. Okay? So the solid line is the one that you want, but you'll get these peaks that occur if there's an air gap. B, film edge extending beyond the phantom. So if the film edge is sticking up, you get issues. If that happens, then your buildup area will be misrepresented. Okay, it'll be incorrect, and it makes sense because if it's sticking out, the depth is going to start somewhere higher than when it's supposed to start. And C, the film edge is recessed within the phantom, so that's the opposite. So if the film edge is inside the phantom, you'll get things that look like this. So issues to consider if you're using film. But we don't tend to use film too much for PDBs. Phantoms. For practical purposes, solid water equivalent phantoms are available for dosimetric measurements. So solid water, requirement for solid water has to have the same electron density, electrons per cc, and the same effective atomic number of water. Okay, and they have their own secret recipes. Different companies make different solid waters. Jimmy and I were looking at the manual of a solid water made by CIRS. CIRS is a phantom company, and there's a manual and they make different types of solid water depending on what energy you want to use. Okay, so the one we were using has an energy range of, was it 50 keV to 100 MeV? It was a pretty big range. And then they have solid water for lower energies, and they have solid waters for a smaller energy range. And that all depends on the electrons per cc and the atomic number of the solid water. Now, if you're using a plastic that's not solid water or not water, and you want to know what the water equivalent depth is, for example, MapCheck. MapCheck has an array of diodes, and then on top of that it has some unknown material. Okay, and that unknown material is approximately, I would say, 1.7 centimeters thick. But the manual tells you that the solid water or the water equivalent depth is 2 centimeters. Okay, everyone's using MapCheck here, right? Okay, and so how do they calculate this 2 centimeters? This is how they calculate it. They know what the R50 of that material, and that material is probably polystyrene or acrylic, some kind of plastic material. They know what the R50 of that material is, because they've measured it, R50 of that material. They know what the R50 of water is, because they've measured it, for that particular energy. So the depth in water is equal to the depth in the particular medium. So if this is 1.7 cm, then the depth in water is going to be 2, because this ratio here would be greater than 1. So that's how they get the value of 2. PDDs for small fields can look different than larger fields. So when treating with small cutouts, it's a good idea to measure PDD. Okay. So as your cutouts get smaller and smaller, you need to consider measuring a PDD for that cutout, because the PDDs do change. And there's a figure in 417 in Khan that shows that. Here we go. So, field size. Okay. So they have 2 energies here. They have an example of an 8 MeV electron curve and then a 32 MeV. This is pretty high, 32 MeV. That's probably from a betatron or something. It's not from a Linac, not from a regular Linac. But anyway, what tends to happen if your field size gets smaller is that your PD starts to come back. Okay. It starts to get shallower and not as penetrating as your aperture gets smaller. Okay, so you want to consider, because if your aperture gets smaller and your PDD changes, yet your doctor goes to your PDD tables, which are defined for an open cone, and there's going to be misrepresentation of PDDs there. Okay, so you might want, because he might look at the table of PDDs that you have for open cones. He might say, well, this tumor is 3 cm deep. And it looks like the 12 MeV electrons cover 90%. so I'm going to choose 12 MeV. Okay? But in fact, that PDD could be different because it's got a different cutout. And so that he might want to choose a higher energy. So what I would do is, the next time I commission a machine or a center, this is what I'm going to do. I'm going to create circular cutouts because we often use circular cutouts to treat tumors, and we just keep them around and we just reuse them. So what I think I'm going to do is I'm going to measure, obviously, the output factors for the circular cutouts, but I'm also going to measure PDDs for the circular cutouts and have a table of PDDs that I can show the doc. Say, okay, you're using this circle, we've got to go to the circle PDD table, and it's going to be a little bit more accurate. Okay, so equivalent square is very difficult to determine due to the scattering. This is again for electrons, due to the scattering properties of electrons. Okay, so equivalent square formula works very well with photons to a point, but for electrons, it's really not a good way of calculating cutout factors. Inverse square correction can be calculated for extended SSD setups with virtual source method, but it's more accurate to measure output with a chamber. Again, why is that? Remember that inverse square correction for electrons? Effective SSD plus D max divided by effective SSD plus D max plus G. That effective SSD value, that's for open cones. Because that value comes from a bunch of measurements that you did when you were commissioning. And you only did those for open cones. So again, you're using open cone data to do an inverse square correction for a cutout. If you're doing it on an open cone treatment, that's fine. But if you're using a cutout, there's a margin of error there. Okay, so if you're doing extended SSDs, it's better. It makes more sense to measure the output factor. It just takes 15 minutes, right? Who's measured output factors here? Electron output factors. Okay. Do you guys still put them in the Bible in the electron cutout? Bible at Lutheran? I started this electron cutout Bible because we were measuring cutout factors for every electron patient, and then I thought, well, why don't we just draw the cutout, write the cutout factor, write the FG, write the cone, and put it in a book, and just keep collecting them, and then eventually we'll have so many cutout factors that can be measured that when one comes around, we could flip through the pages and find one that fits best, and just use the one out of the book. And this book started getting thick over the years, and it was like this thick. Have you seen it?
No.
We call it the Electron Cone Factor Bible. No? Just ask them for the Bible, we'll show it to you. And every time we measure it and we put it in, over so many years, we probably don't need to, because you probably have every size now in that book over so many measurements. So then, with so many measurements, you don't have to take measurements anymore. But they're still taking measurements.
Yeah, it only takes 5 minutes to set up and take it.
Right. Okay, so virtual source method, we talked about this already. Virtual source. Okay. We've already talked about that method. X-ray contamination. So we know that when we treat patients with electrons, there are some X-rays in there, right? Where do the X-rays come from? So I know it's been a while. I think it was the other quarter that we talked about it. Well, electrons are created in the waveguide. They don't hit a target, right? There's no target. They go through this opening, where there would be a target if it was photons. So they go through an opening, but they hit something else. What do they hit?
Scattering foil.
Scattering foil. Okay, so they hit a scattering foil, and when electrons hit metal, what happens? Creates bremsstrahlung. Because that's where the X-rays come from electrons hitting the scattering foil. Number one, of course, they scatter off metal, and they create bremsstrahlung when they scatter off the jaws, and they scatter off the collimator, and so they create bremsstrahlung there too. But most of the X-rays are created in the scattering foil. It's usually not a concern, okay, because it's a small proportion, and actually we can measure how much photons are being created, right? Because if you look at a PDD curve of electrons, it looks like that, and here's the bremsstrahlung tail right there. Those are the X-rays. So we have an idea of how many X-rays are. And typically this is, for the highest energy, the tail is the highest, and it's about 2% for 20 MeV electrons, approximately. Okay, so it's not a big concern. 2% of the dose is not a big concern. What would be the concern if this was a lot higher? Why would that be a concern? Say the tail was, say we just changed physics for 1 second. And we say that's our bremsstrahlung tail. Why is that a concern?
Because you're getting doses from target that's
Yeah, because we're treating superficial tumor and the X-rays are penetrating. So, but since it's only around 2%, we're not that worried about it. But it is a concern for total skin electrons, because for total skin electrons, we only want to treat a couple of millimeters. We're not treating a tumor. We're just treating the skin. So any X-rays penetrating more than that, and we use a lot of monometers because the patient's further away. So the X-ray contamination could be significant because it could contribute to a deeper dose. But how do we mitigate that? Do you know how we get around that? There's a trick we do so the patient doesn't get any X-rays and just get electrons. The trick is this. Most of the X-ray contamination in an electron field is in the center. Okay, because when that electron beam hits that target, the electrons scatter out laterally, but photons go straight. Most of the photons will be concentrated in the middle of the beam. So what we do for total skin is we angle the gantry above the patient so that the central axis points above the patient. And the field is huge because the patient's on the other side of the room. So the patient really only gets treated with half the beam, the lower half of the beam for the top part. And then we point, for the second part of the beam, we point the central axis below the patient's legs. And they get treated with the top part of the beam. And then those add up. Okay. And then we decide on what the gantry angle should be to create an even distribution of dose. Okay, so that's how they don't get any X-rays. Okay, electron, we've talked about this a lot. One new thing here is the D90. You know how I had a rule of thumb for D90 is the energy divided by 4? This is a little more accurate. The D90 is still a rule of thumb, but D90 is energy in MeV divided by 3.2, and D80 is energy in MeV divided by 2.8, and that's in centimeters. D90 in centimeters, D80 in centimeters. Okay. DREF, you guys know DREF, that comes from TG51. Surface dose increases with energy due to quick dose buildup from lateral scattering. Okay, so this is something else you need to know. Surface dose, as in photons, as the energy goes up, they say we go from 6 MeV to 18 MeV. What happens to skin sparing? It get worse. We increase photon energy. Forget about electrons for a second. Photons. You increase skin sparing, right? As you increase the energy, Dmax goes deeper, skin dose goes lower. Okay, electrons is opposite. As you increase electron energy, the skin dose increases. And that's because the higher energy electrons will be able to travel further. Okay, so they can travel further, and so many of those electrons are scattering laterally. Okay, so there's a high, all this lateral scattering, and the fact that they can travel so far adds up. All this lateral scattering adds up. So the higher the energy, the higher the skin dose, because the electrons are allowed to travel further, and they add up. So the electrons that are coming straight down and affecting this part here, that's contributing some skin dose, but the ones that are going here are traveling and adding up to these. The lower energy electrons do not scatter as far, and so they're just local. They just deposit the energy local, and there's not this like summation of skin dose. So with high energy electrons, higher skin dose, low energy electrons, lower skin dose. Opposite of photons. What is RP? You guys know RP, right? Should I go over it again? Okay, RP is draw a straight line from the Bremsstrahlung tail, draw a straight line from the downward portion of the curve, that intersection point, drop a perpendicular, that's RP. We know that. PDDs are sometimes tabulated to get quick quantitative information. Okay, that's good to know. All right, so here's the tabulated PDD. This is not a PDD curve. I mean, you know, when we take a PDD curve, we can tabulate that, and that's just every depth in millimeter increments versus a PDD. This is a little bit more practical. That's fine, but this is also practical because it's a summary of the PDD. And so what we have here is a table with different energies for your machine, and over here are PDD, here are PDDs, and the numbers in the table are depths. Okay, so if the doctor, typically doctors prescribe to the 90%, so if they know that the tumor is 2.4 cm deep, then they make a selection of 8 MeV to treat the patient, to treat that tumor. Okay. If they want to be more sure that they're going to treat, then they might go to 10 MeV because that goes even deeper. Okay, so that's how this table's That's how this table works. And then the doctor also says, well, I want to know if I want to treat with an 8 MeV, I'm treating 90% to 2.4 cm, what's Dmax getting? Or where's Dmax? Well, Dmax is at 1.8 cm. Okay, so that tells them where Dmax is getting, where Dmax is. Okay, so and this goes all the way down to 50. Not all clinics have this table, but it's a nice table to have. And we'll do an example. A doctor wants to deliver at least 90% of the prescription dose to 3 cm in tissue. Using this table, what energy would you suggest?
And
10? Everyone agree? Okay, he wants to give it to 3 cm. 10 goes to 3.1, just a little bit further, 1 millimeter deeper. Great, 10. Okay, 10 MeV, right? Okay, but the doc has another demand. And by the way, the patient's 83 years old and is on the table and in an uncomfortable position, so think quick. This can happen. This is realistic, real life. He says, I don't want the 100% any deeper than 2 cm, because that's where the tumor ends and healthy tissue begins. In other words, the tumor is 3 cm deep, but it only goes up to 2 cm depth, and this is all healthy up here. And he doesn't want the 100% to be any deeper than 2 cm. Okay, so what do? So if we just use that, okay, so he doesn't want the 100% any deeper than 2 cm. Well, 100% is 2.3, so that's too deep. So we can't use 10 now. All right. So if he wants here, let's draw it. So here, there's the tumor. The tumor starts at 3 cm. Okay, so he wants to treat that, and the 2 cm is over here, and he doesn't want the 100% any deeper than this. He wants the 100% up here, because that's where the tumor begins. So if the 100% is here, you'd miss the tumor up here. Okay, he wants the tumor to get at least 100%, at least 90%. So he wants the 100% up somewhere shallower than that. Okay, so we could go to 8 MeV, right? That'll be shallower. But what happens at 3 cm? Wow, look, 3 cm, the tumor only gets around somewhere between 70 and 50%. That's not enough dose. So we're kind of stuck, right? But we can use a trick. We can use bolus. Okay? So, use bolus. So what do we do with bolus? Oh, this is another example. Okay, so what do we do with bolus? What can we do with bolus? So bolus, what bolus does is it increases all these depths by the thickness of the bolus. Okay, so say we use a half cm bolus. Put a half cm bolus here. Same energy, 10 MeV. Now, all these are subtract half cm. Okay, so this is 0.5. Subtract half cm. This becomes 1.8. This becomes 2.3. This becomes 2.6. Okay. So now, what about half cm? Will this work? So half cm, this becomes 1.8. So we've satisfied the 2 cm requirement. This up. No, we're not. We're at 2.8. We're not deep enough. So what's an option?
12.
Let's go to 12. All right. So this becomes 2.5, 2.1. Sorry, it's a little deep still. It's a little deep. Well, what is the 90%? This is okay because we're at 3.1. So we're close. So what about 14? Oh, that's not. That's too deep. So 2.1. So this is pretty close. This option right here, the 12 can be is pretty
Use
close.
a 6 centimeter bolus here at 230.
Yeah. Right. So you can. Problem with 6 millimeter bolus is that it doesn't exist. You can't buy it. Okay.
That's only 0.5 and 1 cm.
Or 0.3. You can get 0.3. Yeah.
So
What about 0.3?
You use 2.
0.3? No, that won't work. What about 1 cm? What happens if you use 1? Well, if you use 1, you're okay here. You're 2.6. You're not okay here. What about here? 14 would work.
Yep.
Yeah, 14 would work. But this might be 2. Oh, 1 cm, then you're at 3.1. Yeah, so you can use 1 cm and go to 14 MeV. Okay, so those are the kind of things that you need to play with, the parameters that you play with when a doctor says, the doctor might give you that kind of detailed information. The tumor starts at 2 cm and ends at 3 cm. And this is the percentages I want to cover with. And you need to play with this table and bolus. If you had the other table, the regular PDD table, it's just too much information. This is a nice table to use for these kind of calculations. All right, let's do some more examples. What energy to deliver 90% to a depth of 2.3? 8, okay. What energy to deliver 95% to a depth of 1.8 cm, but 100%, no deeper than 1.4%? So look at the first one. What energy to deliver 95% to a depth of 1.8? So 95, 1.8 would be 7, but 100% no deeper than 1.5. Okay, this is too deep, so what do we do? Half cm bolus. Okay, so half cm bolus. This becomes 1.3, and this becomes 1.7. Not deep enough, right? How about half cm? How about half cm over here? This becomes 1.8. That's too deep. What about 1 cm? Yeah, what about 1 cm? 1 cm and 8. No, so that's okay. This becomes a 0.8, and 95 becomes 1.2. No, okay. Over here. Oh yeah, that's fine. No deeper. Yeah, no deeper. So 1 cm and 8 would work. Okay. How much bolus is required to bring 5 MeV 100% to surface?
One centimeter?
Yeah, 1 cm. So Dmax is at 1 cm, so you put 1 centimeter bolus, and now you've got 100% at the surface.
So is making a custom bolus not encouraged?
Custom meaning something that you make at different thicknesses?
Yeah.
That's a little tricky. That's a little tricky because first you have to have the anatomical information, maybe from a CT scan, right? In terms of how deep the tumor is. And then you need to ensure that you can make the bolus accurately enough to reflect what's going on internally. Then, once you've got that done, and I don't know how you do that, it's very tricky to do that, then you need to ensure that the therapist will place it correctly every day. You know, because remember, this is a manual. This is a manual interaction. It's not like a metal compensator that goes up in the head of the machine that can only go in one spot. So there's a few sources of error there. So I might have used the custom bolus once or twice, and the way it was custom would be one thickness, like a 1 cm in one place and a half cm in another place. That's as custom as I would get.
So I remember like video when Joggin mentioned like wet gauze as a custom bolus once, but it didn't seem like they encouraged it.
You know, and wet gauze is nice when you can't get bolus in certain places. Let's see, what's an example of that? There's some places that are really small and you can't cut bolus small enough, so you just use wet gauze just to increase. You don't really know how much it's doing, but you know that you need to increase the skin dose, so you just put that on because you know it will increase the skin dose. Electron therapy is not as accurate and not as precise as photon therapy. There's a lot of margin of error, and that's why doctors monitor their electron patients pretty closely in terms of skin reaction. You'll see, because there's a certain amount of uncertainty. Not always, but in certain situations. Okay, we did that right. Electron clinical dosimetry. How many slides do you have? Do you know?
It says 29.
Oh, there it is. Okay, thanks. Electron clinical dosimetry. Isodoses tend to follow shape of patient contour. Bolus is often used to bring maximum dose. We know that, and there's the count, which we've talked about before. Cone factors are measured. We've done all this. We've done this. We've done that. Typical run. Okay, we've done all that. Irregular fields. So I talked about cutting and pouring. Obtained from either direct measurements. We've talked about that. There's a little bit of redundancy in this talk. Cutout factor. Talked about that. Output factor. MU must be measuring treatment SSD. That we've talked about. Let's do an example. If you take a reading with a chamber and electrometer on the machine, the treatment cutout, in a 5 by 5 cone using 6 MeV electrons and 110 SSD and get 1.2 nanocoulombs. You remove the cutout, set up to 100 SSD and take another reading and get 1.5 nanocoulombs. The prescription is 180 centigrade to 90. What is your cutout factor and what are your MUs to treat this field? Okay, so if you're treating with an extended SSD, remember how I just a little while ago I recommended to take the measurement if it's an extended SSD rather than doing the inverse square formula, because the inverse square formula is for open cones. Well, this is an example of how you would take the measurement. So it's an extended SSD because we're treating at 110. And the way you take your measurement is you take a first measurement with the treatment cutout in a 5 by 5 cone, then remove the cutout, set up to 100 SSD, and take another reading. Now, this is your cutout, and this second read, by the way, this divided by the second reading is your cutout factor. That cutout factor includes your inverse square, right? Because you're taking one reading at 110 and another reading at your reference SSD. So that includes your inverse square factor. You don't need an inverse square. That's more accurate than using the inverse square formula. Okay, so the inverse square factor is built into this guy. Okay, so what is the cutoff factor? What do you think, Don?
So it'd be 0.8.
Yeah, it's 1.5 divided by, 1.2 divided by 1.5. Okay. And then what are the MUs? Mm-hmm. I'm going to put the 1.0 times 90% because that's prescription.
Factor.
Okay. What was that, 0.8?
Yeah.
Okay. Do I need inverse square? Okay. Why do I need this if I've got this? Why do I need this if I've got this?
Because you did open and block field for the same cone. So you don't, if you had done the reference cone and the 5 by 5, you would have included that factor. But
Okay. Yeah, because this is relative to a 5 by 5. But a 5 by 5 does not have a dose rate of a 1.0. Only 15 does. Okay, so we need this to relate the 5 by 5 to the 15. Okay. So if you had no time to measure and had to calculate the inverse square factor, you would use the virtual source method and include the correction in your MU calc. And there was the formula for that. There's the answer. 268. And that's something else to keep in mind in terms of monitor units. Whenever you do an MU calculation, always look at this number and say, does that make sense? Does that make sense? For electrons, this number here is typically going to be pretty close to the dose for electrons because your cutoff factors are really close to 1, your cone factors are really close to 1. When they're going to be different than the dose, extended SSD, definitely it's going to be different than the dose, and if your cutout is really small. So for electrons, to do a sanity check of MUs, it's pretty easy. Because really those are the only two confounding factors. Extended SSD is going to make MUs a lot higher, and your cutout is going to make the MUs a lot higher. Otherwise, you can pretty much say that the MUs are going to be just a little bit higher than the dose. Okay? So if the dose is 200, MUs are going to be like 205 or 210. Okay? So it's really easy to do sanity checks on electrons. If you had no time to that'd be good. Okay. Patient collimation, we already talked about this when treatment is very small. So if the area is very small, what's small, by the way? You know what the cutout should be for electron cutouts? how it shouldn't. You shouldn't make a cutout smaller than a certain amount. First, what's the disadvantage of making a really small cutout, like a 1 cm circle? What's the disadvantage of a 1 cm circle? Cut electron cutout. The dose distribution becomes Gaussian. Okay, with an open cone, the dose profile distribution, it looks pretty flat, right? We've seen them, right? Go up, and flat, and come down. As you get smaller and smaller, it becomes Gaussian. Okay, Gaussian looks as a bell curve, right? So what's the problem with Gaussian? The problem is, here's a patient's skin, and here's the light field of a small cutout. There's a light field. But the dosimetric, and the light field looks like it might cover a certain area that the doctor wants to treat. The doctor looks at the light field and says, yeah, it's a really small tumor, that's what I want to treat. But in fact, the dosimetric distribution looks like this. It doesn't look like the light field. Okay? So the center is going to be, this is just because of the way electrons scatter. The center is going to be really hot and the sides are going to be cold. So remember that when you're doing small cutouts. Now I would say you don't want to get smaller than 3 cm. Okay, that's my cutoff. But some tumors are smaller than 3 cm. So what do we do? How do we treat smaller tumors? How do we treat 1 cm tumor with electrons?
You can use a larger cutout and use something to block them.
Yeah. So you use a small cutout, like a 3 cm circle. And then you place lead. So you use a 3 cm. I'm going to exaggerate. That's 3 cm. And then you put a piece of lead on the patient. That's 1 cm. And bingo. Now, your distribution looks like that. Okay. And you can prove this to yourself with film in the clinic. And when you have some extra time, take a piece of GAT film, look for a small cutout, or make a small cutout, shoot the film with a really tiny cutout, and then repeat it. Make a little lead cutout with a larger electron cone. Repeat it with the lead cutout, and compare your distribution in the scan, grid or whatever. You can prove it to yourselves if you have time. Okay, so this is much better because then the light field does represent what you're going to treat. Okay, good. So instead, use a larger cutout, place lead aperture on the patient's skin. Okay, a rule of thumb for lead thickness to reduce dose. Then the question is, how much lead do you use? So a rule of thumb to reduce the dose in this area by 95% under the lead. The rule of thumb is the energy. So say the doctor's picked 6 MeV divided by 20 centimeters. Okay, so just to make it simple, if the energy is 10 MeV divided by 20, so it's you need a half cm of lead. Okay. And it's hard to cut through, make a hole in a half cm of lead. So what most clinics have is really thin sheets of lead, less than a millimeter, and you just stack. You just cut a little hole and multiple sheets, make sure the hole is the same size, and then just stack them, and that creates your thickness. Okay? 12 MeV requires 0.6 cm. So 12 MeV requires 0.6 cm. All right, and here's a graph of what happens when electrons scatter off the edge of lead. So if you were to put lead right on the patient's skin without any kind of lead wrapping meaning wax around the lead, this is what the isodose distribution looks like. So here's this hot spot, 127%. 100% being here looks like 1.5 cm or 1.8 cm. 127 is this hot spot right here. And this is in water, by the way. And they've kind of parameterized this. They've looked at, you see how the curve, there's a hump here, where the curve would otherwise just be straight. There's an enhanced dose due to the lead, so it increases the dose here. So they've parameterized this by following this hump and calling this angle theta. Alpha. Calling this angle alpha. Okay, and beta, I'm not sure where beta comes from. Maybe it follows. I'm not sure where it comes from. But probably follows this curve here, where the dose drops off. So this 127% hotspot situation can occur when using lead placed on the skin. Avoid this by wrapping it with wax. Now, angle alpha decreases with an increase in energy. So this angle will decrease. That angle is 50. So which angle is it? This would be this way. So this angle is going to increase this way as you increase in energy. The dose, however, increases with energy. So with an increase in energy, alpha is going to go this way, but the dose increases with energy, so this hump is going to get bigger. So it just gives you an idea of what happens to the dose when you put lead on the surface. Okay, and then obliquity. Obliquity is something else you want to avoid at all possible. But it's hard to do in many cases, and in a lot of cases we do treat with obliquity, but we need to be conscious of what would happen. Like if we go in there to help the therapist set up the beam, and there's no other way, there's going to be some obliquity, we need to know what's going to happen, and we need to tell the doctor, you know, this is what you should expect. And what they expect typically is if the beam is angled in this direction is that there's going to be a hot spot right here. Why is that? Because that has the shortest SSD. All these other points here have a bigger SSD than this point right there to the cone. Hey, I made it stop. So areas of the patient closest to the cone will receive higher doses. Obliquity does three things. It increases side scatter, okay, because now the electrons aren't coming orthogonal, they're coming at an angle, so it increases side scatter. Decreases the Dmax depth, decreases the penetration of dose. 1422 as an example, let's look at it. Let's look at what happens when there's beam obliquity. It's right here. Yeah. So this is a nice graph that shows you what happens. So see what happens. There's a big peak. This is at 60 degrees. I mean, that's a big angle. But look, let's look at 30. What happens is that the curve, you lose your penetration. So the curve starts coming back towards the surface, and Dmax starts getting high. So those are the two things that happen. Surface dose gets higher, Dmax gets higher, and you'll lose your penetration. So the dosimetric effects of obliquity only occur at angles greater than 45. So that's a lot. That's a big angle. So for most cases, we don't have to worry about that. Okay. Okay, this is another graph that just proves the same thing. This graph on the left is 9 MeV electrons. This is 15 MeV electrons. And here's the alpha, the obliquity angle. And so here's what happens. The curve just gets pulled back towards the surface. Okay, and then you lose your penetration. So for a certain depth, the PDD is a lot lower. Okay, and then you calculate that beam obliquity. I mean, I threw this in because I think it might be in the textbook. And so what happens is, remember how Dmax and your curves go more shallow. So now your 90% is more shallow. So where you think, if a doc wants to deliver 90% of Dmax, and the beam is oblique, the Dmax dose might not be 100% anymore, it might be 95%. And so you need to roll that into your calculations. But you don't have to worry about this. This really doesn't happen. Actually, because you don't know this number very accurately. It's very difficult to know that number accurately enough. So it's typically not a correction that you would do. So the MU calc, you throw this 0.95 factor because of obliquity in there. Okay, what about abutting fields? So this is an example of 19 MeV electrons. On the left-hand side, we have 92 SSD. On the right-hand side, we have 97 SSD, different field sizes. And this is just an illustration that shows what happens when you abut electron fields. And this is pretty common because sometimes you want to treat a large area and one cone does not suffice. So you need to use two cones side by side. So the first thing the doc will ask you is, how much gap do we use? Are you going to use a gap calc? Are we learning with photons? No, nothing to do with gap calcs, because that gap calc depends on depth, and we're not treating it at depth. So you need to know this kind of thing. So the doc will say, well, how much gap are we gonna apply to this patient? Well, let's look at this. If there's a half cm gap on the skin, look at what happens. Because of the gap, the dose up here is colder. Okay? But as you go deeper, you get 120% hotspot. Why do you think that hotspot is there?
Because the lateral scattering.
Yeah, there's more lateral scattering. But I don't know if I have any PV curves. No, sorry, profile curves. But with low energy electrons, if you look at profiles or actually I should call them isodoses. Low energy electron isodoses for a single beam looks somewhat like this. So this is the 90%, 80%, 70%, and 100% might be up here. 100%. Okay, so this is like a 6 MeV electron beam. Okay. Now, if we take a 20 MeV electron beam, it's going to look like this. It's like a bell. Okay. And as it gets to RP, and the energy starts dropping, they start to scatter sideways more. Okay. And so the isodoses look more like a bell for 20 MeV. There's more side scatter at deeper depths, not at shallow depths, but at deeper depths. That's where the 120 comes from. These two, this one here, abutting with another one that's next to it, the bells are going to add up. The diverging isodoses are going to add up. Okay, that's where that comes from. All right, let's look at a 1 cm. So the doctor might say, no, this is too cold up here. And I want to make sure I treat that area. Okay, well, let's make the gap smaller. But as you make the gap smaller, you're satisfying one requirement to increase the dose here, but down deeper, you're going to have an issue because you're now at 130%, which may be a hot spot that the doctor is not comfortable with. Let's close the gap even smaller to make sure that this is cold, that this is no longer cold. Now you're at 150, and that's just because you're just adding up these two divergent bells. Okay, you're just adding them up, and it's getting hotter and hotter. So, which one would you guys pick? What do you think makes more sense? And so if this were 6 MeV, would we have this issue here? No, it wouldn't be as bad. What's a possible solution for this? And there is a solution.
If you do the first one, you can do a third field with a small aperture targeting the cold area.
Okay.
If you're using low energy, you won't penetrate down to the hot spot.
That's a really small field, though.
That would be a small
Yeah.
field.
Yeah, that's a possibility. You would really have to have a good grasp of the isodose lines that are going to add up to those to do that. What's another possibility? It starts with an F. Well, first of all, would you do this option? Okay, we don't want to do that with this high energy. How about this one? That's still too high. Right. The doc would be a little concerned about that. But might be okay. I mean, depending on the, also it depends on the total dose, because 130% seems crazy. It seems like a really high dose. But what if the doc is not going to a very high dose? 130 might not be that unreasonable. So this is a possibility. But let's say we go with this possibility. How do we avoid this cold spot?
Can we just use a bolus to bring the cold spot into the bolus?
So if we put a bolus, I mean, put a strip of bolus right here.
Yeah, up there.
Okay. So that would bring the isodoses up, right?
Yeah.
Mm-hmm. That could do it. Yeah, we could do that. That's one possibility. What would happen down here?
It would get
It
colder.
would get colder. Yeah. That could work. Mhm. I would probably want to do it with film first. You know, like line them up with a centimeter gap, put a piece of bolus, and shoot it, and look at the film and see if that worked. Because it's non-conventional, what you just mentioned, is something that people don't tend to do. So anything non-conventional, I would do a dry run, a dosimetric evaluation. Okay, what's another possibility? Feathering. You guys heard of feathering? Oh, okay, sorry. Feathering is when you have two fields that abut the intersection line where they match. That match line, we're going to move it during the course of treatment. So we're going to start that abutting line at one point, and after a certain amount of dose, say 1,000 centigrade, we're going to move that half cm to a cm. Okay. So say we move it a half cm, that intersection line is going to move a half cm, and we continue to treat the patient to another 1,000 centigrade. Then we move that line again. Okay. And what happens is it blurs out this cold spot. So for 1,000 centigrade, yes, that is cold. But that spot will then move over here where this was not cold. Okay, so that'll blur out. It'll be cold, but not this cold. This whole area will be cold, but not this cold. This whole area will be hot, but not that hot. Okay, so that's actually more common. That's the most common method of abutting fields is to feather. But I like your suggestion of the bolus. That might work too. So feathering makes everybody more comfortable because you're blurring that out. Now, how do you feather electron fields? Well, with electron fields, you've got a cutout that you've made. To feather that, you need to make a different cutout for each feather because you don't want to move the electron cone around. Because if you do, then the other part of that being treated, this part right here, that's going to shift too if you move the cone. You don't want to shift that. So what we do is we just recut the cutout in this area so that for this cutout, the match line ends up here over here, and for this cutout, it ends up there. So we make different cutouts for every match. Okay, so that's one way of getting around that issue. But now, what about abutting electrons with photons? Now, this top one is we can see an electron field up here at 100 SSD, and we see an electron field on the left and a photon field on the right. And down here, we have an electron field on the left again, and a photon field, but at a different SSD, at 120 SSD. So, what are the issues? Same thing. What's the energy here? I think there are 9 MeV electrons. Same thing. There's a little bit of spilling over here into the photon field. If the electron field wasn't here, this hot spot would be here. Okay, so we're getting a hot spot due to the electron field. So when we abut, it occurs when treating the IM chain. So the inframemory chain, that's when you have photons coming in this way, but you put an electron strip here to treat some nodes that are way over this side here. So now you're abutting electrons and photons when you do that. And electrons scatter outwards and add to the photon dose, which explains this hot spot. The fields are usually matched to the skin. The physician accepts the hot spot. That's typically what's done. Applying a skin gap can produce a cold spot superficially, and an increase in SSD worsens the effect due to the spread of electron beam. So the reason there's 2 SSD here is just to illustrate that the hot spot is worse for the higher SSD. And it's worse for the higher SSD because the electron, remember that divergence I was telling you about? As the SSD increases, it gets worse. Okay. So increased SSD, that hotspot gets worse. Typically, a physician will accept that hotspot. Okay, between electrons and photons. Total skin electrons. We talked about this a little bit. Lymphoma with symptomatic skin. Symptomatic skin means that the symptoms show up as red blotches on the skin. It looks like a bunch of. If it's not an advanced case, it just looks like a bunch of mosquito bites. If it's advanced, the whole skin can be red. Called mycosis fungoides. Treat at about 350 centimeters SSD with 6 fields per day. The entire body is covered with 2 fractions in 2 days. Okay, so let me just explain this a little bit more because I don't know if that's clear. We need to treat the entire body: front, sides, back, underarms, eyelids, feet. What we don't want to treat, there's a couple of things we don't want to treat is fingernails, toenails, and the eyes. Okay, so how do we protect that? We protect the fingernails by putting little pieces of lead, and we do this every day. We wrap the patient. We tell the patient, we're giving you a manicure. So we wrap the patient's nails with lead and the patient's toenails with lead. And then the eyes are blocked with eye shields. Have you folks seen internal eye shields in your clinics yet? The internal eye shields look like a round, like a half shell. It's about this big, 2 centimeters in diameter. And there's a little handle on the end that's made of heavy metal, tungsten, usually tungsten. They'll pull on the eyelid and stick it inside, and the eyelid goes over these shields. And then that protects the eyes, but you can still treat the eyelid. So those are the shields we use. The other thing we do is, since the patient's going to be standing for a while, and by the way, they're not wearing any clothes, because any clothes that you wear will attenuate the electrons. So they're standing there with no clothes on, and they can't see. There's a possibility that they could lose their balance. So I built this harness from a mountain climbing harness. So I bought this mountain climbing harness at REI, and then I went up into the ceiling, and we put these metal beams into the concrete. We drop straps from the metal beams, and we attach the straps to the mountain climbing harness. And then when the patient's ready, we kind of tighten it, not too tight, but we just tighten it, and it's to prevent the patient from falling over. Okay. So also their blood pressure tends to drop when they're up there because of the radiation and just maybe the whole the anxiety of treatment. So those are some issues. Those are some things that we do to protect the patient. Now treatment. Treatment again. This is the one I was talking to you about treating with two fields where the central axis is way above the patient and the other field is below the patient. So that covers an AP field. So there's two AP fields, upper and lower, and the patient stands like this. Since we have to cover the stuff, if the patient were standing AP like this, we would miss all of this stuff, and we'd miss the inside of the legs. So they need to stand like this, and they need to have one arm here and one arm like this. Walking like an Egyptian. Okay, so the first field is AP, and AP is like this. The second field is an LAO. Okay, that's when they turn their legs this way. They raise one arm here and they do this. That's an LAO. Okay. And then another one is an RAO. Okay, and that's starting from AP. They raise this arm and they turn their feet this way. And that's an RAO. And that way we can cover the inside of the arm, the inside of the legs. The same thing for the back. PA, and they just repeat. Okay, so there's 6 positions that the patient has to be in, and there's 2 fields per position. So that's 12 fields total. Now, you do not want to treat an AP, an RAO, and an LAO on the same day, because you're adding up the AP with the LAO and the RAO. So there's this addition of dose that happens, and so we want to avoid that. So on the first day, we treat AP, and we treat an RPO and an LPO. And then on the second day, we treat PA and the 2 anterior legs. So one fraction is 2 days. And each field is a double field. It's an upper and lower. So that's what the Stanford total skin electron technique, that's how it works. There's a lot of physics that goes behind the scenes in terms of calculating the dose rate that we measure, that we treat with. And you can use TG51 or TG21 to calibrate. But remember, you're not calibrating with a phantom on the couch. You're now calibrating over at 350 centimeters. Because the energy of the beam degrades from the LINAC all the way to 350. It degrades because the electrons interact with the air. Okay, so let's see, do I talk about energy here? So low electron energy is used because you just want to treat the first couple of millimeters. So we treat with 6 MeV electrons. By the time it gets to the patient, it's degraded to around 3 MeV. And some places actually use a little. They put a piece of acrylic, a 1 cm thick piece of acrylic sheet, in the head of the machine to degrade the energy even further. Okay. So field overlap. We talked about degradation of beam energy, beam spoiler distance. Dual fields used for treatment, avoid photon component that exists in central axis. So I talked about all that. So summary, we talked about basic concepts today. Bless you. We talked about measuring PDDs, electron contamination, monitoring the calculations at different depths, at different prescriptions. Remember the 90%, etc. Skin collimation with lead. What happens with oblique fields? How do we handle budding fields? And we talked about total skin treatment. Okay, so we covered a lot today. This was a lot more detailed than the first time we covered electrons. Any questions, discussions, disagreements? Okay.